All right, so today we're diving into something really cool, a brand new AI that's making some incredible waves in what's known as a grand challenge of computer science. That's automated theorem proving. So let's get into what this actually means and why it's such a massive deal.
You hear this all the time, right? AI can reason. But what does that really mean? See, most of the time when we're talking about large language models, we're talking about something very, very different from the kind of hardcore step-by-step logic you need to prove a mathematical theorem. And that's the real test.
Okay, think about it like this. On one hand, you've got informal reasoning. That's us, chatting. It's creative, it's intuitive, but let's be honest, it's not always 100% precise. Then, on the other hand, you have formal proof. This is pure, cold, verifiable logic. Every single step has to be proven. There is literally zero room for error, and that is what makes this a grand challenge for AI. And it's a place where most AI models just fall flat.
But, that entire landscape is starting to shift, all thanks to a new model that is just tearing up the rulebook. So, let's introduce the hero of our story today, GOEDEL-PROVER-V2. It's a new series of open-source models designed from the ground up to conquer this incredibly complex world of formal math proofs. And this is where things get absolutely insane. Just look at this chart. On a key math benchmark, the reigning champ was a monster of a model with 671 billion parameters. But then comes GOEDEL-PROVER-V2 with only 8 billion parameters. I mean, that's not just a little smaller, that's over 80 times smaller, and it actually beats the bigger model. This is a classic David versus Goliath situation. So how on earth did they pull this off? Well, the secret sauce here wasn't just throwing more computing power at the problem. No, the researchers behind this built a smarter model, but using a powerful combination of 3 key innovations. So what's this winning formula? Well, it boils down to 3 key parts: scaffolded data synthesis, verifier-guided self-correction, and something called model averaging. Let's break down exactly what each of those fancy terms means. Okay, first up, scaffolded data synthesis. Think about how you teach a human student math. You don't throw calculus at them on day 1, right? You start with basic algebra. This technique does the exact same thing for the AI. It generates and feeds it math problems that get progressively harder. You're building this solid foundation, step by step, which lets the model eventually tackle insanely complex theorems. All right, number 2 is verifier-guided self-correction. And if you're a programmer, this next one is going to sound super familiar. You know how you write code, run the compiler, and it spits back a bunch of errors for you to fix? Well, this is basically the same idea, but for mathematical proofs. The AI uses a formal verifier called lean to check its own work, find its mistakes, and then it corrects them. It learns and gets better with every single try. And finally, the third secret ingredient is something called model averaging. You can think of this like creating a super expert by combining the knowledge of a bunch of different specialists. By merging different versions of the AI model from various points in its training, the final product gets a much more diverse toolkit of problem-solving strategies. It makes it way more flexible and a lot less likely to get stuck on a tricky problem. Okay, so that's the theory, that's the winning formula, but how does it actually perform in the real world? Let's take a look at the leaderboards, because the results, they are something else. So on the MiniF2F benchmark, the results are just dominant. They use a metric called pass at 32. All that really means is, how many problems can the AI solve if you give it 32 tries? The 32 billion parameter version of GOEDEL-PROVER-V2 already hits 88.1%, totally crushing the old record. But then, when they flip on that self-correction feature we talked about, it jumps all the way to over 90%. That is a huge jump. But if you thought that was impressive, hold on. Things get even crazier when we look at the Putnam competition. For anyone who doesn't know, this is a legendary, ridiculously hard math competition for college students. The best previous open-source model solved 47 problems. GOEDEL-PROVER-V2 solves 86. That's nearly double. And look at this. It did it with way fewer attempts, which means it's not just better, it's way, way more efficient. Let's just pause on that number for a second. 86. That's not just a little better. That is a whole new level for what we thought was possible for AI in one of the toughest intellectual fields out there. Okay, so it's a math genius. That's awesome. But what does this actually mean for the rest of us? Why should you care? Well, there are 3 really big takeaways here. First off, it's a huge reminder that bigger isn't always better. Smart design and clever training matter more than just raw size. Second, this is a massive win for open source. Because the researchers made everything public, the entire community can now build on this, which just speeds up progress for everybody. And maybe most importantly, this is a huge step toward an AI that can actually reason in a way we can trust and verify.
I mean, the researchers behind this said it best themselves. They see their work as helping to bridge the long-standing divide between intuitive human reasoning and formal proof verification. They're not just building a calculator on steroids. They're trying to teach a machine how to think with a kind of logic that's absolutely bulletproof.
And that really is the big question this leaves us with. We're watching an AI begin to master a domain of pure logic that was once exclusively human. So if formal logic isn't the barrier it used to be, what's next? What are the other grand challenges that are suddenly on the table? It's a question that, thanks to this breakthrough, is more exciting to ask than ever before.